Jai Hind everyone. Myself Dr. Pankaj Goel, working as an assistant professor in Akgec Engineering College. Today we will discuss another important topic, that is oxidation. The content of today's discussion are introduction to oxidation, need of oxidation, oxidation techniques, thermal oxidation introduction, thermal oxidation types, dry, HCl, wet and high pressure oxidation, then plasma oxidation, oxidation properties and silicon oxidation model, that is Deal and Grooves model. So, that will be the content of today's presentation. Okay. First of all, what is oxidation? So, oxidation is a process of forming a thin layer of silicon dioxide on the surface of a silicon wafer. This is a critical step in the manufacturing of semiconductor devices, because silicon dioxide is used as an insulator, it is used as a protective layer or as a dielectric in various stages of Vlsi fabrication. So, there are multiple uses of forming a oxidation layer on the surface of the wafer. That is, it acts as an insulator, it acts as a protective layer and it acts as a dielectric. Here in this figure it has been shown that how the silicon wafer looks like before the oxidation takes place and after oxidation takes place. So, we can see that on the top of the silicon there is a SiO2 layer is formed, and this was the original interface, original silicon interface. So, SiO2 layer is formed below as well as above the original silicon surface. Here in this figure it is more clear, the original silicon interface has been shown as a dotted line here, and when oxidation takes place, then SiO2 layer is formed below the interface as well as above the silicon surface. So, that is the thickness of the SiO2 layer. Now, the need of oxidation. In bipolar and MOS transistors, it isolates one device from another. Okay. So, oxidation layer is actually behaving as a insulator and it isolates different devices. Secondly, the oxidation layer acts as a barrier or mask against the diffusion or implantation of impurity dopants in the substrate. As we have also discussed in the case of lithography, that we used to create the windows in the substrate, so that at the desired locations doping can take place, and at all other locations, in all other areas where windows are not cut, doping cannot take place, because there is a silicon dioxide layer over the surface of the wafer. Third, in most devices it acts as a component. And fourth, it serves as a dielectric isolation between multi-level interconnect layers. As we know that in case of Vlsi ICs that we develop, either we have a large surface area over which we can do the interconnection, but the drawback of that is the size of the chip get increased. So, what we do multi-layer interconnection, where the different interconnecting layers are isolated from each other by creating a layer of SiO2 between them. Okay. Now the oxidation technique, the thermal oxidation first. See, in this case, thermal oxidation, oxygen diffused through the oxide to the boundary of the silicon and silicon dioxide, and the reaction takes place there. And when this SiO2 layer is formed in a typical thermal oxidation process, it has been observed that almost 46% of the oxide layer appears within the original substrate and 54% of the remaining layer on the top of it. So we can say that here this is the original interface, this is the original interface, and 46% of the SiO2 layer is below this original interface or the original surface of the silicon, and 54% is above. So it is like this. So this is a typical value. 46% of the SiO2 layer is formed beneath the silicon surface and 54% on the top of it. Now, the thermal oxidation technique can be further divided into broadly two types: dry and wet oxidation. Dry and wet oxidation. In wet oxidation, we use oxygen as well as water vapors to oxidize the silicon, and in dry oxidation, we only use oxygen, that is, we do not use water vapor in this case, dry oxidation. And the advantage of dry oxidation is it produces a denser, cleaner oxide layer. There is a comparison of wet oxidation and dry oxidation. See, in case of wet oxidation, we use water vapor and the temperature is used between 900 degrees centigrade to 1000 degrees centigrade, whereas in case of dry oxidation, the environment is oxygen, there is no water vapor involved. So in the oxygen environment and at a temperature of about 1200 degrees centigrade, oxidation takes place. The reaction, the chemical reaction in case of wet oxidation is silicon plus 2H2O give you SiO2 plus 2H2, whereas in case of dry oxidation it is in the oxygen environment, so Si plus O2 will give us SiO2. So wet oxidation is typically used to grow thick oxide layer, which is also known as field oxide layer, whereas dry oxidation is used to grow thin oxide layer. It is because the rate of oxidation in case of wet oxidation is high, whereas in case of dry oxidation the rate of oxidation is low. Now, some more information about dry oxidation. Here, as we know, the dry oxidation takes place in oxygen environment, and there is another variant of dry oxidation that is known as HCl dry oxidation. Here, along with oxygen, we use HCl also. Why we use HCl is because using HCl help us protect from sodium ion contamination. If we are working in an environment where there are sodium ion contamination that can take place, so to make sure that sodium ion contamination does not take place, we provide HCl dry oxidation. In this case, the sodium ions get reacted with the HCl to make it aqueous solution, 2NaCl and H2 gas. So this aqueous solution can be, this byproduct can be removed, so it does not contaminate our silicon wafer. Okay. Wet oxidation, there are further, it can be divided into two types. Wet oxidation can take place either using pyrogenic technique or bubbler technique. There are two techniques by which wet oxidation can take place. In the first one, the pyrogenic technique, H2 and O2 molecules are used to form the water vapor, and this technique assure high purity steam, and provided high purity gases are used. If we provide high purity hydrogen and oxygen gases, it assure the high purity steam. Okay. Now, in the bubbler technique, the second technique, we provide the water vapor. We don't provide H2 and O2 separately, we provide the water vapor. This water vapor are introduced into the oxidation furnace to oxidize the silicon at high temperature, and this technique uses a bubbler to generate the steam. In this case, we also use oxygen or nitrogen as a carrier gas to transport the water vapor into the furnace. What is bubbler? A bubbler is a container with water that is kept at a specific temperature. When the carrier gas is passed through this water, picking up water vapors into the process and take it to the silicon wafer where the oxidation takes place. Now, the effect of temperature and pressure in oxidation. It has been discussed previously also that there are certain drawbacks that are associated with high temperature processes. If we do any Vlsi fabrication process at a high temperature, the movement of previously dopants takes place, which is known as out diffusion. The dopants that are there in the substrate at high temperature, the movement of those dopants takes place and they may come out of the substrate and can be deposited in the oxidation layer. So, this is an undesired result and we should avoid it. Now, there is a way to avoid it, is doing our oxidation process at a low temperature. But if we do our oxidation at a lower temperature, what will happen? The rate of oxidation growth slows down. So, the growth time is more. So, that is the effect of temperature, that at a higher temperature out diffusion takes place where the already diffused dopants come out of the substrate and they get deposited in the oxidation layer, which is an undesired result. So, if we do our oxidation at lower temperature, its drawback is the growth time is more. It takes more time to grow a layer of SiO2 on the surface of the silicon. Now, let us see the effect of pressure. Now, if the pressure is increased, say by 1 atmosphere pressure, we can do our oxidation at the same oxidation rate by decreasing the temperature by 20 degrees centigrade. So, reducing the temperature by 20 degrees centigrade and increasing the pressure by 1 atmospheric pressure, there is no change in the growth rate of the oxidation layer. So, the reduction in temperature get compensated by increase in pressure. So, the high pressure oxidation with pressure up to 25 atmospheric are used in the industrial applications at temperature in the range of 700 to 900 degrees centigrade. we have seen that previously, that in typical applications of dry and wet oxidation, the oxidation temperature is used around 1000 to 1200 degrees centigrade. So, the pressure has been reduced to 700 to 900 degrees centigrade in case of high pressure oxidation techniques. This figure explains the high pressure oxidation results. Here we can see that if the atmospheric pressure, if the oxidation is taking place at a higher pressure, say here the value is 1 atmosphere pressure and here it is 20 atmospheric pressure. Here it is 1 atmospheric and here it is 20 atmospheric pressure. So, at a higher pressure, the oxide thickness is more in a given time. Here the time is given in hour. So, in a given time, the oxide thickness is more if the pressure is more. Here we can see the oxide thickness is in micrometer. So, at a higher pressure, in a given time, oxide thickness increases. So, the oxidation rate is more. Now, the next technique that we have to discuss is plasma oxidation. Up till now, we have discussed the thermal oxidation technique and its variants like dry oxidation and wet oxidation. Then wet oxidation is further of two types, the pyrogenic technique and bubbler technique, and then there is another variant of this is high pressure oxidation. Now, the next technique is plasma oxidation technique. Now, see, the advantage of plasma oxidation process is it offers the possibility of growing high quality oxides at temperature even lower than those achieved with high pressure techniques. So, we know that the high pressure oxidation takes place at around 700 to 900 degrees centigrade, but using plasma oxidation even at further lower temperature we can do the oxidation and that will give us high quality oxides. So, the temperature that may be used for oxidation in case of plasma oxidation technique is less than 600 degrees centigrade. So, let us see what a plasma is. Plasma refers to an ionized gas that contains a mixture of charged particles such as ions and free electrons along with neutral atoms or molecules. In a plasma, the reactive oxygen species such as O plus ions, O radicals and electrons are much more chemically active than neutral oxygen molecules at the same temperature. The high energy of these species allow them to interact with the silicon surface and oxide it at a lower temperature than traditional thermal oxidation. Okay. So, lower temperature is used for oxidation because of high energy of these ionized plasma species. So, plasma oxidation is a low temperature vacuum process usually carried out in a pure oxygen discharge. The plasma is produced either by a high frequency discharge or a DC electron source. Now, placing the wafer in a uniform density region of the plasma and biasing it positively below the plasma potential allows it to collect actively charged oxygen species. The growth rate of oxide typically increases with increasing substrate temperature and plasma density. Now, what is a high frequency discharge? High frequency discharge is typically having a frequency of about 13.56 megahertz. Okay, and this high frequency electric field is used and what it does is it releases the electrical energy through the gas which sustain the ionization process, and maintain the plasma. The alternating electric field accelerate the free electrons in the gas, and these high energy electrons collide with the neutral gas molecules, knocking off electrons from these molecules and ionizing them. The advantages of this plasma oxidation technique is low temperature processing, high quality, thin oxides, and uniformity. These are the important advantages of plasma technique. Okay. Now, a typical oxidation system contains a horizontal furnace in which the wafers are held vertically in a slotted paddle, or also known as boat. Typical temperature range from 700 to 1200 degrees centigrade. The wafers are chemically cleaned, dried and loaded into the paddle and inserted into the furnace at a temperature of 700 to 900 degrees centigrade. Now, why we have mentioned that the temperature of the furnace is initially in this range is because the temperature is then slowly ramped up to the oxidation temperature. Say if the oxidation takes place at a temperature of around 1100 degrees centigrade or 1200 degrees centigrade, then the temperature is increased slowly. Why? Because otherwise wafer warpage may take place. What is wafer warpage? It is the deformation of a silicon wafer into a saddle shape. That is, your silicon wafer bends like this. This is known as saddle shape. The silicon wafer at a higher temperature, if the temperature is suddenly increased very high, then it get bend and it is known as saddle shape. So, to avoid this wafer warpage, initially the temperature of the furnace is kept at around 700 to 900 degrees centigrade, and then slowly it is ramped up to this value. This is the oxidation system, a typical system which consists of a horizontal furnace in which the wafers are vertically kept on a slotted paddle. Okay. Now, oxide thickness and oxide technique. What is the role of oxide thickness in choosing a particular type of oxidation technique? That has been discussed here. See, if the oxides are relatively thin, then it can be grown in a dry oxygen environment. And if there is sodium ion contamination, we have discussed also, we can use dry HCl environment. But if we need thick oxide layers, then in that case we have to use steam, that is wet oxidation. Okay, now the next topic that we have to discuss is the oxide properties. Okay, the first one is masking properties. We all know that silicon dioxide acts as a barrier or mask against the diffusion of dopant atoms at high temperature. This is a very useful property, and to act as a mask, the thickness of the oxide layer typically is in the range of 0.5 to 0.7 micrometer. Okay. So, to act as a barrier or mask so that the dopants cannot be infused inside the substrate at undesired locations, the thickness of the oxidation layer at those places should be in the range of 0.5 to 0.7 micrometer. For different dopant atoms, the diffusion constant in silicon dioxide is different. Okay, and diffusion constant actually decide the oxidation thickness, oxidation layer thickness. So, this is a value of diffusion constant for different kind of dopants. So, here we can see that the value of diffusion constant is highest for gallium, whereas for others it is comparatively lower. So, the definition of diffusion constant is that it is a parameter that characterizes how easily atoms or molecules can diffuse through a material. Now, the second property of oxide is oxide charges. There are four kinds of oxide charges that are developed when the oxidation takes place. They are the interface trapped charge, fixed oxide charge, oxide trapped charge, and mobile ionic charge. And all these four type of charges take place in the transition region, that is at the interface of silicon and silicon dioxide. So, at this interface, these four kind of charges may be found. This is a diagram representing different kind of charges, oxide charges. So, this is our silicon, this is our silicon dioxide, and this is the interface. And at the interface, it may not be SiO2, it is SiOX because of the incomplete bond at the interface. So, let us see the first kind of charge, that is interface trapped charge. Now, these charges are associated with the imperfections at the interface, such as dangling bonds. What are dangling bonds? Dangling bonds are nothing but the unbonded atomic bonds. These are the unbonded atomic bonds where one or more bonding partners are missing. That is, the bonds are not complete, one or more bonding partners are missing, and so these unbonded atomic bonds, which are known as dangling bonds, result in interface trapped charge at the Si-SiO2 interface. Similarly, it may also happen from structural defects or stress from lattice mismatch. The second kind of charge is fixed oxide charge, and it is caused by structural defects such as number 1, oxygen vacancies, or number 2, excess silicon atoms. If at the interface in the silicon oxide layer there is excess of silicon atoms or there are oxygen vacancies, in that case the structure does not remain neutral in nature. So, the charges are developed. So if the cause of charge is excess silicon atom or oxygen deficiency, then that kind of charge that is developed is known as fixed oxide charge. Now the third kind of oxide charge is known as oxide trapped charge, and it happens if the carriers such as electrons or holes become trapped in the defects within the oxide bulk layer. Okay, if these charges such as electrons or holes get trapped inside the oxide layer, then these kind of charges are known as oxide trapped charge, and it may happen because from the ionizing radiations or high currents. Okay, we know that we provide ionizing radiations or high currents in case of plasma oxidation. The last type of oxide charge is known as mobile ionic charge, and these charge are developed inside the SiO2 layer because of the contamination from mobile ions such as sodium ions, potassium ions or other alkali metal ions. So if these kind of mobile ions are in the vicinity such as sodium, potassium or other alkali metal ions, these ions in the oxidation layer cause mobile ionic charge. The third property is oxide stress. Now we know that when silicon dioxide layer is developed over the surface of silicon, then the thermal expansion of Si and SiO2 is different, and because of different thermal expansion of silicon and silicon dioxide, it result in stress, it result in creation of stress. So also the second reason of this stress creation at the interface of Si and SiO2 is when the windows are cut into the oxide. When windows are cut into the oxide, it results in a complex stress distribution, and these high stress levels have the possibility of structural damage in the silicon. So oxide stress should be minimized. Now quickly we will discuss the last topic of today's presentation, that is the Dill and groove model. We know that this Dill and groove model is a silicon oxidation model which describe the kinetics of silicon oxidation. This model is generally valid for temperature range between 700 to 1300 degrees centigrade and partial pressure between 0.2 to 1.0 atmospheric. For oxide thickness between 300 and 20,000 angstrom for oxygen and water ambients both. Now here we can see this figure. This is our silicon and this is our oxide. So this is our interface, Si-SiO2 interface. Okay, and this is the gas phase. Gas phase. Here this is the D represents the thickness of the oxide layer. Now C is the concentration of oxygen at a particular instant. Here like it is the Cg. Cg is the concentration in the bulk of the gas. Cs is the concentration at the gas oxide interface. C naught is the concentration of the oxide at the interface of gas and oxide. Ci is the concentration at the interface of silicon and silicon dioxide. Okay, further we have three kind of flux, F1, F2 and F3. Now, when the oxidation takes place, then in that case the oxidizing species are transported from the bulk of the gas phase to the gas oxide interface with flux F1. With flux F1, this is F1, and then inside the oxide layer they are transported across the existing oxide toward the silicon with flux F2. Okay, inside the oxide layer the oxide species are transported to the silicon interface with flux F2, and at the silicon dioxide interface the reaction taking place with flux F3. And for a steady state all these flux must be same, F1 equal to F2 equal to F3. Now the flux F1 can be approximated as proportional to the difference between the oxidant concentration in the bulk of the gas, that is Cg, and the oxidant concentration adjacent to the oxide surface Cs. So it is flux is given by Hg into Cg minus Cs, where Cg is the oxidant concentration in the bulk of the gas and Cs is the oxidant concentration at the oxide surface, and Hg is the gas phase mass transfer coefficient. This is the expression for F1. Similarly, we see here now Henry's law is used here to relate the equilibrium oxidizing species concentration in the oxide to that in the gas phase. By Henry's law, C naught is equal to H into Ps and C star is equal to H into Pg. Now first of all let us see what is Henry's law. Henry's law is a gas law that describes the relationship between concentration of the gas dissolved in a liquid and the partial pressure of that gas above the liquid. That is, the gas concentration that get dissolved in the liquid is proportional to the partial pressure of the gas above the liquid. So more the partial pressure above the liquid, more the gas that will be dissolved in the liquid. So that is the Henry's law and that has been invoked here. Now in this expression for Henry's law, C naught equal to HPS, where H is the Henry's law coefficient, H is Henry's law constant, and PS is the partial pressure in the gas adjacent to the oxide surface, and C naught is the equilibrium concentration in the oxide at the outer surface, whereas C star is the equilibrium bulk concentration in the oxide, and Pg is the partial pressure in the bulk of the gas. Okay, so we can see the concentration in the bulk of the oxide, that is C star, is proportional to the partial pressure Pg in the bulk of the gas. So that is C star equal to H into Pg. Similarly, C naught equal to H into Ps. using Henry's law along with the ideal gas law, we get F1 equal to H into C star minus C naught, where H is the gas phase mass transfer coefficient and is equal to Hg upon capital H into K into T, where capital H is the Henry's constant, K is the Boltzmann constant and T is the temperature in Kelvin. Now, similarly, the flux F2 inside the oxide is given by D into C naught minus Ci upon D naught, where capital D is the diffusion coefficient, D naught is the oxide thickness, Ci is the oxidizing species concentration in the oxide adjacent to the oxide silicon interface. Now, the flux F3, that is the reaction rate at the silicon and silicon dioxide interface, is given by Ks into Ci, where Ks is the rate constant of chemical surface reaction. Now, after setting all the three flux equal in a steady state condition and solving the equations, the expressions for Ci and C naught can be obtained, and in this situation there are two limiting cases that are arises. There are two limiting cases that are arising is when the diffusivity is either very small or very large. When the diffusivity is very small, in this case Ci will be equal to 0 and C naught will be equal to C star. This case is called the diffusion controlled case because the diffusivity is small. So, the rate of diffusion decide the reaction. In the second limiting case, where diffusivity is very large, Ci becomes equal to C naught, and this is called the reaction controlled case, because in this case, because of diffusivity is very large, there is abundant supply of oxidation, and the oxidation rate is controlled by the reaction rate constant Ks. And by Ci, which equals C naught. So, this is about Deal and groove model. Thank you very much. The content has been taken from the book Vlsi Technology by McGraw-Hill Education. The author name is SMC. For detailed study, you may refer this book. Thank you very much.